Is
I'm gonna go
Joey
ahead
with you?
and record my presentation just to let you know. So,
Good.
hello, everybody. My name is Dr. Tamie Jovanelly, and I am so happy to put this presentation together. I've had a lot of fun in doing it. And I originally was thinking about inviting the people who have already gone to Iceland with me and the people who are going on the trip. And then I realized I'm part of this Facebook group that has to do with Iceland geology. And so I put out a Facebook call to see if anybody would want to join. So we have a lot of people that are geologists on this call. And we also have a lot of STEM teachers. My former student, Mallory Polk Stone, now is one of those. So we have a very broad audience. And so what I'm going to do is I'm going to ask that you hold your questions to the end and that you put them in the chat. And then at the end of the presentation, I'll come back and take a look at your questions. The talk is meant to be at an introductory level, and our conversation can get more complex from here. But what I'm going to talk about is past and present fissure eruptions. And the reason why I wanted to put this together is because I think it's neat to put things into a historical context to look at what has happened previously on the island and compare that to what's happening today. So some of you might be curious as to how I ended up in Iceland in the first place. So my first trip to Iceland was in 2006 when I was setting up a study abroad program for Berry College geology. And like most geologists, once you visit Iceland once, you look for a reason to go back. And so I've been back pretty much every single year since 2006. And in doing that for more than a decade, I looked down one day and I had this crazy idea of writing a book. And so I did. And so I published this advanced geological concept book about Iceland in 2020 with Wiley. And it's separated into three major parts, focusing on the tectonics, the volcanics, and then the glacial features. And the reason why I did that is because that's very much how I conceptually think about the island. So I think about the implication of tectonics, how that relates to volcanism, and then how the glaciers come and ruin it all. So in writing this book, I had a great time. I loved it. And so now I'm writing my second book for Oxford University Press, and it's going to be a general text about volcanoes. So look for that to come out in the next couple of years. When I was going on these study abroad trips, I would always come back and people would ask me, Dr. Joe, when are you taking us to Iceland? So in 2019, I decided to launch a tour company, and it was originally called Iceland Geology Tours. And now we've rebranded and expanded, so it's called Adventure Geology Tours. So we go to Iceland and we go to a lot of other amazing places. But my favorite part is that I get to experience Iceland with different people who love geology as much as I do. And before we get started, there's one more thing that you need to know, and that is I don't speak Icelandic. Although I practice with really good intentions. Thank you, Google. You've heard that it's a pretty complicated Nordic language. So I'm going to apologize for my mispronunciations in advance. And this is a talk on geology, so you're going to see some acronyms on my slide, including MYO, millions of years old, MYA, millions of years ago. And all of the drone footage that you're going to see within this lecture is going to be part of our personal collection. And so I hope that you appreciate this natural beauty as much as I do. So just to give us some general background about the island of Iceland, since we're all coming from different points of knowledge, we're going to start with a modern day plate tectonic diagram that you see on the screen. I'm down here in the great state of Georgia on the purple North American plate, and Iceland is sitting at approximately 66 degrees north latitude. Iceland is approximately 38 miles south of the Arctic Circle. It's bordered by the Arctic Ocean to the north and the cold, dense, and saline waters of the Atlantic to its south. And the island of Iceland is conveniently located on top of a divergent plate boundary. And so we have the Eurasian plate here in orange, and that's moving, pulling, or spreading apart from the North American plate. Another unique feature of Iceland is that there's also a hot spot or a mantle plume and it's currently about 200 miles in diameter, and it's sitting underneath Europe's largest remaining glacier called Vatnajökull. And Vatnajökull at modern day takes up about 14% of the island of Iceland. The geological history of Iceland is pretty unique. It starts at approximately 50 million years ago when you have the origin of that hotspot. And what ends up happening is you have these effusive basalts that build up on the bottom of the seafloor to create what we call the Icelandic basaltic plateau, which is the island of Iceland. So the oldest rocks that we see on the island of Iceland are approximately 33 million years old. So if we consider the age of the Earth to be 4.6 billion years old, Iceland has barely had a birthday. And it is this divergence that really sets the dynamic stage for the island. On this map here, you'll see the divergent plate boundary highlighted in red. The Eurasian plate is on the right. The North American plate is on the left. And at modern day, these plates are pulling, rifting apart at a rate of about 1 inch per year, or 13 miles per million years. I'll repeat that because that's your fun fact. So you have these plates that are pulling or spreading apart at a rate of about 1 inch per year, or 13 miles per million years. And so you have this dynamic tectonic setting in addition to a hotspot underneath the island. And in combination with these two systems, when we look at the island of Iceland, it's about the size of the state of Virginia. So you have this island that's approximately the size of Virginia, but it has 33 active volcanoes. So anywhere you look in the Iceland landscape, you either see an active volcano, a dormant volcano, or some type of volcanic feature. This map shows you the proximity of those 33 active volcanoes. And so I'm going to give you a second and take a closer look, because I want you to focus in on the position of where these volcanoes are. And if you do that, hopefully a pattern should begin to emerge. And when you look at the position of these 33 active volcanoes, what you should be able to tell me is, Dr. Joe, these volcanoes outline the position of the divergent plate boundary. And that makes a lot of sense, doesn't it? So when you have divergence and spreading, you're creating a conduit for magma to more easily come up to the Earth's surface. And when you have a magma plume, highlighted with this yellow star, you also have a generation of more magma to stimulate activity on these different volcanoes. When we focus on volcanoes in Iceland, we separate them into three major parts, whereby talking about the northern volcanic zone, the western volcanic zone, and the eastern volcanic zone. Some of the biggest and baddest volcanoes on the island of Iceland, and really arguably in the world, are in the eastern volcanic zone along the southern coast of Iceland. I'm going to call your attention to number 15. She's one of my favorite volcanoes, and her name is Katla. She'll show up later in the presentation. But where the volcanism is happening from 2021 to 2024 is on this area over here on the western coast that's called the Rainies Peninsula. And the volcanism that we see at modern day are termed fissure eruptions. But what exactly is a fissure eruption? So by definition, a fissure eruption occurs when linear underground passageways, called dikes, get infilled with magma.
Gotta make a bun. Oh yeah, gosh, of course.
And when we talk about fissure eruptions particularly, we separate them into two major groups. So I'm going to call this scenario 1 and scenario 2. I'm going to ask that you pay attention closely to these diagrams because I'm going to reference them throughout the talk. So up here at the top, we have scenario 1. And what is happening is you have a magma reservoir, and that magma reservoir is being fed by the mantle. So you've got deep material that's coming up through the Earth system to fill a magma reservoir. But this magma reservoir is directly attached to a magma chamber. And that magma chamber is underneath a large central volcano. And off of this magma chamber, you have these linear underground passageways that will get infilled with magma. So this is describing what I'm calling scenario 1. Scenario one has some predictability. And the reason why it has some predictability is because most of the magma chambers underneath major volcanoes in Iceland are pretty well researched. So geologists have a pretty good understanding of their size and shape and the volume. So you have some idea of the capacity of magma that they can hold. So you have an understanding of how much magma is being fed to these linear underground dike systems. In addition, in scenario one, usually the dikes are relatively shallow. So they're only between 2 and 4 miles below the surface. So that means that geologists, using a variety of different instrumentation, can really monitor these as magma reservoirs in addition to. So oftentimes, especially in Iceland, when you have an area that has a central volcano and also a fissure, this is a great area to harness geothermal energy because of its predictability and because it's so close to the subsurface. In scenario two, you can have the presence or absence of a volcano, but more importantly, we're focusing our attention on this magma reservoir. So the magma reservoir is directly linked to the mantle, and the magma reservoir directly feeds this fissure swarm system. So it's directly feeding these linear underground passageways with magma. We would say that scenario two has less predictability really for two reasons. One, because theoretically, the magma supply is unlimited. And two, usually these linear dike systems are much deeper within the earth. So it's a lot harder for instruments to be able to physically monitor where the magma is in the subsurface in this scenario two type of system. When we talk about a fissure eruption, we tie this to something that's called a fissure swarm. I'm calling your attention again to this map on the screen. We've already looked at it once when we identified those 33 active volcanoes outlining the divergent plate boundary. But what I want you to do now is I want to focus your attention on the position of these red dots, because these red dots represent central volcanoes, scenario one. But what we also see on this map is scenario two, and that's highlighted in light blue. So when we tease out the volcanics of the island of Iceland, with specific to these 33 active regions, what we find is that 14 of the 33 active volcanoes in Iceland are designated as fissure swarms. So about half are scenario one and about half are representing scenario two system. With either, in pretty much all of these volcanic regions in Iceland, the Icelandic Meteorological Office is monitoring for activity. The Iceland Meteorological Office is the equivalent to the United States Geological Survey in the United States. So it's a really great clearinghouse for a variety of different type of geologically related data. And what they monitor for when looking at these fissure swarms is they're looking for two main characteristics. They're looking first for something called the ground surface inflation. And that makes sense, doesn't it? So as you have magma that's coming up to the surface to infill these linear passageways, you're increasing the volume and you're going to have expanse of the ground surface as a result of that. You're going to have uplift. When we look at this diagram over here to the right, on the x-axis, you're seeing days. And on the y-axis, you're seeing uplift or ground surface uplift or deflation in terms of millimeters. So this is looking at one of the fissure eruptions in 2023, just to give you an example. And when we focus on the top diagram, you see that there is no inflation of ground surface. And then all of a sudden, you start to see a slow and steady increase up to 400 millimeters. 400 millimeters is equivalent to about 1.3 feet. And then what will happen is that eventually the magma will breach the surface. You'll empty the magma chamber, empty the subsurface dike system, and then your ground surface will go through deflation. And that's what we're seeing in this bottom diagram. So you can end up with actual subsidence on the surface, Sometimes your dike systems will even collapse on themselves when they become empty. So we can look for inflation and deflation, and then we can also look for earthquake activity as a precursor to a fissure swarm. And that makes sense too. So when you have magma that's moving up to the Earth's surface, it's filling in these cracks and crevices of the Earth's crust, and it's going to release low-level seismicity. Not to say when we think about Iceland, there's always some low-level activity because you have that divergent plate boundary. But more importantly than the energy that's being released, it's the amount of earthquakes that we see recorded prior to a fissure eruption. So you can have more than 10,000 earthquakes occurring in a specific area that acts as an indicator that something's about to happen. When we look at this diagram here, it ties into that 2023 inflation deflation record that we just saw. Each of these individual dots represents an earthquake event. So lots of movement of subsurface activity prior to the magma breaching the surface. When we look at, and so what's going to eventually happen is when you have a fissure eruption, you're literally creating a crack in the Earth's surface. So you literally have spreading that happens, and that allows for a conduit for magma to come up easily to the surface. The type of magma that we're looking at these fissure eruptions are called basalt, similar to like a Hawaiian island event. We call them mafic because they have a low silica content. And this mafic magma has low viscosity and low resistance to flow, so it gently flows onto the surface of the Earth. And oftentimes, these are referred to in Iceland and in Hawaii as tourist eruptions because you want to be able to appreciate this natural beauty. And because of the low viscosity and the non-explosiveness of them, you can generally get quite close to this type of volcanic event. And you can really get as close as you can really withstand the temperature. Iceland Meteorological Office does a great job at monitoring these different fissure eruptions to keep their people and also the tourists safe. So you'll have people walking around the perimeter that are scientists, and they're monitoring for gases. And so if gas levels get too elevated, then they'll be sure to move people around. But you can see how close Joey is cooking our dinner as we're viewing one of the 2023 eruptions. And I think what's fun to think about is the Vikings and their relationship to all of this volcanism. So remember, the hotspot, this isn't new. The hotspot's been around for 50 million years. The island is built from this type of effusive eruptions. And when we talk about volcanism on the island of Iceland, we say that there is one volcanic event every 5 years. So the recurrence interval is one volcanic event every 5 years. So if you meet somebody that's Icelandic and they're 100 years old, they've lived through 20 different volcanic episodes. So nothing new. The Vikings established themselves in Iceland at 874 CE. And when they did, there was a lot of fissure eruption activity that began. So the Vikings, in their sagas, when they talk about these fissure eruptions, they refer to them as fires or curtains of fires. And so when we look at this picture, we really have an understanding and appreciation of what they were seeing in 874 CE that's very similar to what we're actually experiencing in 2024. These beautiful curtains of fire as the magma comes to the surface. What's also interesting is when you read some of these past sagas, the Vikings really are pretty nonchalant about volcanic activity. The early Vikings were pagans, the others migrated to Christianity a little bit later, and they really took this non-religious viewpoint, really not fearing these fires, even though they truly did not understand them, but really appreciating them for their natural beauty and remembering the early Vikings were nomadic. So if a fissure eruption is happening for too long, they have a whole entire island of which they can explore and resettle. So they really took on this idea of like, this too shall pass, and really kind of working within that natural system that makes Iceland so unique. When we talk about fissure eruptions, they do not typically form a central volcano. Instead, what happens is they do form something that's called a vent. When we look at this video here, this is from a Bardabunga eruption in 2019. What we see is that there's two different vents that are forming. And vents are forming because there's localized pressure within the dike system. So it's forcing more magma to the surface at these localized areas. Vents are also referred to as spatter cones. And they're called spatter cones because if you look closely at these eruptions, you see the magma that's going up in the air, and as it's falling down to the surface, it's cooling, and it's cooling as tiny particulates that's called tephra. And I have some tephra. I don't know if this is going to work, but I'm going to hold it up to the camera. And so they're just tiny pieces of magma that falls to the ground. And so it becomes unconsolidated. And so you find that around the perimeter of these vents, also called spatter cones. When we talk about fissure eruptions, lots of times in the media, they like to describe the fountain and the discharge. So when they are talking about the fountain, they're talking about the height of the magma as it's coming to the surface. So usually if there's more pressure and if there is an abundance of magma in the system, you're going to have a taller fountain. And then similarly with the discharge. So the discharge represents how quickly the magma is moving on the surface of the earth. Similar to like if we talked about the discharge of a river system, we can talk about the discharge of the magma at a fissure eruption. In addition to in the intensity, we can talk a lot about the duration. And this is what's truly interesting, is that it can be really different for a variety of different reasons. So you could have a fissure eruption last 2 days, a week, years, decades, or even centuries. So there's a lot of variability, and most of that variability really depends on how much magma is being stored in the reservoir and how much magma is being supplied over time. So speaking of intensity and duration, I wanted to focus my attention on 3 historical eruptions. And I think this is fun to do because it gives us a comparison of what we're seeing here in 2024. So the first one I want to describe is called the Mývatn fires. And the Mývatn fires happened 800 years after the Vikings settled, from 1724 to 1729. And Mývatn fires are up here in the northern volcanic zone. So they're tied to scenario 1 because they have a central volcano, and her name is Krafla. And so just like scenario 1, where you have the volcano, you have a very shallow dike system just off of that magma chamber. Krafla is one of 5 different fissure swarms in the northern volcanic zone. And during this event, what happened is that there was a pastor that was living near Lake Mývatn, and he made great historical records of this 5-year event. So it's one of the very first true records of an entire fissure episode in Iceland. Lake Mývatn is known for a lot of different reasons. It's a pretty big and interesting tourist spot. So if you've been with me to Iceland, we've certainly been there. We're going to go there this summer. But if you visit Iceland, it's a beautiful destination. And one of the things that makes it unique is that there's not many lakes in Iceland, for one, but for two, this basin of the lake was completely created by historical fissure eruption. And as the pastor writes in 1724, the dimensions and basin shape completely changed as a result of this magma that was coming to the surface. So the lava field ended up covering about 18 square miles within this area. When you visit Lake Mývatn, you can still see the church where the pastor was taking his notes. His church survived, but four farms that were very nearby ended up perishing in the fissure eruption. So maybe it was prayer, but it was more likely elevated topography that ended up saving the church. So if you visit Iceland, you can take a look at what a 1700 church might look like in Iceland. Now, moving forward, buckle your seatbelts, folks, because we're going to talk about the Lackey fires. The Lackey fires occur from June 1783 to February 1784. So we're talking only 9 months. And this was 9 months that wreaked havoc on Iceland and in Europe and really globally. The Lackey fires are considered to be the worst natural disaster in Iceland. And when you look at history books that are given to the students, they talk about the Lackey fires. So it's something very much part of the Icelandic history that's still communicated. And the reason why it's communicated is because there was a fissure eruption that happened in the eastern volcanic zone, so down here on the southern coast. And remember, I called your attention to number 15, volcano number 15, and her name is Katla. And Katla is part of a scenario 1 type of fissure swarm. But what you can imagine, in June of 1783, there was a fissure eruption that begins to occur, and it opens up a fissure that's 15 miles in length. What? A fissure opens, and it's 15 miles in length. And along this fissure eruption, there's going to be 130 of those different vents that begin to form in a very linear type fashion. So along this crack, there's 130 different vents that begin to form, very similar to what we saw in the video of Bartabunga. So this picture here gives you an aerial image of what the Lackey crater rows typically look like. This is a photo that's from Thor Thordarson, and he wrote a fantastic paper that you can find on Google Scholar. He published it in 2023, and he talks in detail about the Lackey fires. So when you have a fissure that's 15 miles long and you have 130 different vents that are beginning to form in only 9 months, you're bringing a lot of magma to the surface, to the tune that Thordarson estimated to be 42 billion tons of magma that's coming to the surface in the course of 9 months. This is going to be the second largest basalt flow in recorded history in Iceland. So what happens when you bring 42 billion tons of magma to the surface? You have a lot of problems. Now, what's interesting is that Lackey fires are going to be completely different than anything else we talk about in this lecture. And the reason is that Lackey fires are originating in the eastern volcanic zone near volcano Katla, but they're happening in close proximity to Vatnajökull, the glacier. So when the magma is coming to the surface, it's interacting with glacial water. And when you have magma that interacts with glacial water, you end up with something that's called a phreatic eruption. So when you have magma mixed with water, it's a phreatic eruption. So you get an explosion that's intensified. And when it's intensified, you can end up with a lot of volcanic ash, which is really uncharacteristic of fissure eruptions as a generality. And because you're bringing so much magma to the surface, you have a lot of volcanic ash. Looking at this diagram, what it's representing in orange is where the volcanic ash went. So approximately 90% of the island of Iceland was covered with ash. But wait, there's more. Not only is there volcanic ash, but the volcanic ash contains fluoride. And that's a big problem, because when that volcanic ash goes up, it's going to fall down and it is going to contaminate all of the ground surface. So the problem is that there's cattle, and the cattle are going to graze on the grasses, and the grasses are now exposed to that fluoride. So the cattle are now going to pass away because of fluorosis. The volcanic ash is going to go into the clean river systems. The water is going to become contaminated with fluoride. The people are going to drink the water, and they're also going to come down with fluorosis. In addition to this, there's a lot of volcanic gases that are going up into the atmosphere. So not only do you have carbon dioxide, but you have carbon dioxide and SO2. And so you have all of these respiratory issues. And in addition, you have fluorosis. And then later, it's going to turn into famine, because nothing's going to be able to grow on the surface. So this is considered to be Iceland's worst natural disaster because 1/5 of the Icelandic population, which wasn't large in the 1700s, late 1700s, is going to perish. So it had drastic implications on the island of Iceland. But as you can imagine, again, what goes up can also be transported and circulated in the air column. But what also happens is that when you read documentation in Europe, they talk about an acid haze that occurred. And right, so we're talking 1783, 1784, there's no cell phones, there's no internet. So all they know is that this acidic rain is coming to Europe and falling onto their ground surfaces, and that's going to destroy their crop. So in Europe, it's thought that there was drastic famine that was spread, again, because of this volcanic eruption. And some historians even say that the Lackey fire eruptions could have been the cause to initiate the French Revolution, because what we know about the French Revolution is that people were hungry. And this could have been one of the reasons why the famine was in place. Because you have, as Thordarson writes about in his paper, there's approximately 120 megatons of sulfuric acid aerosol that was released in the course of 10 episodes. But wait, there's more. So this volcanic ash that goes up into the atmosphere and this sulfuric acid that goes up into the atmosphere is going to eventually be a blocker of solar radiation. So it's going to block incoming solar heat from the sun. And this might be a little bit counterintuitive because when we think of greenhouse gases, carbon dioxide, carbon monoxide, methane, SO2, we consider them to be warming the planet. But a transaction happens when you have SO2 mingle with water vapor that's in the air. And so it switches to sulfuric acid, H2SO4. And that in the atmosphere is going to inhibit solar radiation from coming to the Earth's surface. So temperatures globally are estimated to drop 5 degrees for 5 years after the Lackey eruptions, 5 degrees Fahrenheit. And what's fun to look at is this graph over here to the right. I live in the state of Georgia, so I'm in the eastern part of the United States. And so looking at some records that were published by Thornton himself in 2023 paper, they were looking at global temperatures and specifically looking at how they decrease. So in eastern Georgia, this 5-degree temperature decrease is really important because it's the difference between freezing and not freezing. So in lots of places in the world, during this late 1700s, they talk about famine, and it could have been related to a decrease in global temperature, again, relating to this fissure eruption that only lasted 9 months. Moving forward, another really fun thing to talk about is the Krafla fires because they were more recent. So these fires happened from 1974 to 1985. These are also in the Northern Volcanic Zone, and this is 250 years after the Mývatn fires. But again, the Krafla fissure system is going to heat up again, and it's going to begin erupting. In this, there's going to be 9 different rifting episodes over the course of 9 years. But what's interesting is that these are happening at very short intervals. So on the order of just a few days, up to at maximum only about 2 weeks. And that's the very last fissure eruption that occurred in 1984, and it lasted for about 15 days. So another thing to keep in mind about the Krafla fires is that this was the very first fissure eruption in Iceland that was instrumentally monitored. And the reason why it was instrumentally monitored is because they were building a geothermal power plant. So just like the Mývatn fires and just like the Lackey fires, the Krafla fires are also related to scenario 1, where you have that central volcano and you have this linear dike system that's relatively shallow. So it's only 2 to 4 miles below the surface. And so it's really good for harnessing heat. So they picked a great spot. But those fissure eruptions began in June of 1974. They were slated to open later that year. They took a little bit of a hiatus, but in true Viking nature, they decided this too shall pass. We're going to move on, and they opened up the power station in 1975, and it's still operational today.
Excuse me, if you're calling in or if you're listening, could you please mute your microphones?
Here we are at modern day, and there's been modern fissure eruption activity on the Rainies Peninsula. So I'm going to locate us with a star, and that's going to show us the position of the capital city of Reykjavik. About 200,000 people live in the capital city. And I'm going to give you a second location, and this is Keflavik. And Keflavik is where the international airport is. So if you fly in Iceland, you land at Keflavik and you take a 1-hour bus ride to get you to Reykjavik. And this area here is called the Rainies Peninsula. Now, what I want you to notice is that there's 6 different fissure swarms that are in echelon with one another. And what you should also recognize is that there's no central volcanoes. So we're dealing with a scenario 2 situation where you have deep-seated mantle magma that's infilling these subsurface dikes directly. I also want you to notice that this hashed band that moves through represents that divergent plate boundary. So we can refer to this area as the Western Volcanic Belt or the Rainies Volcanic Belt, but we still have divergent activity that's happening. So we still have active spreading. And I can say that I don't know that I've ever been in the city of Reykjavik where I haven't felt some type of low-level earthquake activity. And usually it's low-level, magnitude less than 4 or less. But there's always continually some type of shaking that's going on just based on the presence of the divergent plate boundary. The last fissure eruption that happened on the Rainies Peninsula was about 800 years ago. And these are called the Rainies fires, and they're named that because they're in the Rainies fissure swarm. And one of the features that you can take a look at if you're in Iceland is what's called Stamper Crater Row. So Stamper Crater Row was the result of the Rainies fires that happened from 1210 to 1240. So this fissure was awake for 30 years, for 3 decades, creating these 2 different vents, but we can see many more off into the distance. I like to show this video because you'll remember that initial creation of the Bardabunga vents that I showed you earlier. This is what they look like once they solidify. We talked about tephra. You see that unconsolidated tiny pieces of basalt in and around the flanks of these spatter cone volcanoes that exist in the landscape. And this gives you a great perspective of what the Rainies Peninsula looks like. And lots of times it gives you the feeling of being on the moon as a result of there being very little vegetation. So moving forward in time, when we look at the modern day activity that's happening, it's happening in the fissure swarm that's called Fagradalsfjall. And the very first eruption occurred in 2021. But what I told you is that in all of these volcanic areas, the Iceland Met Office is continually monitoring. So in 2019, the geologists realized that something was stirring underneath Fagradalsfjall because they were noticing an increase in seismicity and slight increases in inflation of the ground surface. The last time that this area was active was 6,000 years prior. So again, when we look at the Rainies Peninsula, the last eruption on the Rainies Peninsula was 800 years ago. But within the specific fissure swarm, Fagradalsfjall, it was about 6,000 years. And what happened was on May 19th, there started to be a fissure that opened. The good news about the positioning of Fagradalsfjall is that it is a completely uninhabited area. And so we mentioned that in Iceland, like the government and the Iceland Met Office really promotes these as being tourist eruptions. And this was just a spectacular place to view because it's uninhabited, so you don't have to worry about communities being in danger. But also when we look at this map to the right, you can see that it's a topographic map. you can see where the lines are closer together. So you can see that there's these upper elevations that are great vantages to be able to view the spectacular show that a fissure eruption presents to you. This particular eruption lasted 9 months. Sounds familiar, right? But not nearly as devastating as Lackey Crater. Another thing I want to mention that is sometimes confused in the media is the naming of specific fissure events. So again, this fissure eruption is happening in the fissure swarm named Fagradal's Fajal. However, this particular event is often referred to as Glendagalur or Miradalur. And that's because this area, again, is uninhabited. And so they're naming the position of the fissures based on the topography. So they're naming them after the particular valleys that have been impacted by this lava flow. So Glendagalur is the initial place where the fissure opened, and then it's spreading north into Miradalur. And these effusive eruptions are really just following the flow of the topography. So they're going around topographic highs and they're looking for topographic lows. The area in purple represents that lava field. It's 3 square miles. So very different than that Lackey that had a really long fissure and produced a lot of havoc. This was actually a beautiful example of a fissure eruption that a lot of people were able to enjoy. This map here is showing you the overall thickness of the deposits, with the warmer colors being less thick and those that are purple are being part of the thickest parts. So in this area where there is the thickest flow, there's 6 different vents that began to form. And so that makes sense. You're bringing a lot of magma to the surface in that particular area. And it's up to and about 400 feet thick in this area that's highlighted in purple. What I want to do now is I want to show you a drone image of this lava field. So you can see the proximity of this star. This is where we're flying from and we're going to fly up valley. So when we say that this area is uninhabited, it's really uninhabited. So it's a pretty desolate landscape, pretty classic Icelandic internal landscape for the Reynis Peninsula. The dark black, of course, represents that 2021 lava flow. You can imagine these being like lava waterfalls as the lava is going down these inclinations. Off into the distance, you can see some of the vents that begin to form. So it really gives you a perspective of how this magma is coming to the surface, and it's really just following the topography that's already set in place. So moving forward in time, there was 2 more fissure eruptions that happened on this same fissure swarm. The next one is going to be in 2022. And this activity began July 31st and lasted less than a month. So it was in August 21st where it concluded. And my husband and I were lucky enough to be leading 2 groups for the Association for Women Geoscientists when this activity was going on. And after the trip concluded, my husband and I were able to visit these fissures as they were active. Again, they're neatly constrained in Glendagalur and Miradalur valleys. There seems to be a trend with this particular fissure cycle in that we started at a low flow rate and we're steadily increasing. So now the initial flow rate of that magma, the discharge coming up to the surface, was about 1,100 cubic feet per second. This lava flow in 2022 that's highlighted in orange is on top of the 2021, and it represents an area of about a half a square mile. I mentioned, and I'm going to show you a drone video. I'm going to show you a drone video that we took of this lava field. This is a vent from the 2022 eruption. And what you'll notice is, and how we have this slowed down, is you can see this tiny pieces of magma that are forming and cooling in the air and falling to the bottom. And so those are tiny pieces of tephra. The other eruption that happened was just to the north of the 2022 eruption site. This particular eruption is referred to as Little Her, and that's because of this elevated hill here. So you've got a highland topography, and this 2023 eruption, again, only lasted less than a month. Initial flow rate much higher, 1,800 cubic feet per second, but again, a small lava field that will eventually merge and flow down valley to meet the Miradollar. In this particular eruption, there were elevated SO2 and carbon monoxide coming to the surface. Joey and I, my husband, we were able to visit this site when it was active. And what I want you to recognize is that this is not Disneyland, folks. So you park in one of these parking lots and you hike on uneven terrain all the way to get here. So this distance is about 10 miles, 10 hard miles. But what you need to know is that it's absolutely amazing when you get there because you get to see things like this. So this was on the 21st of July, and we're seeing the formation of a brand new vent. You've got a little bit of a breach here, and when you have a breach, you're allowed to form a lava channel, and that's exactly what this is beginning to form. So lava channels are usually forming close to the vent where you have higher discharge and hotter magma. So when you look at magma, the color is an indicator of temperature. So as an example, if we see the color orange, the temperature of that lava is about 1,652 degrees Fahrenheit. The ones that's a little bit more gold in the center of the vent, the temperature is closer to 2,000. So you get this warm magma that flows out of the base of the vent, and it begins to melt the pre-existing basalt, and you end up with these spectacular channels. Off in the distance, what you can notice is it looks kind of like fire or smoke, and it is. So the mosses have caught fire. You can notice that we're in a really good position as we're taking this video because the wind is moving down gradient. So we're really in no harm of the gases. And this is a very extensive channel, again, following the path of least resistance. And we're filming from the top of Little Her, that elevated topography. So the moral of the story is if you're going to hike 10 miles to go see a volcano, you might as well stay the night because that's where the real show is. So this is the evening of July 21st. This is the same vent. You can see that the breach has continued at the base of the vent. Quick discharge still. And another thing that I want to point out is maybe some of you have been to Hawaii, or maybe some of you have been with me to Iceland, but this is the initial formation of a lava tube. So you first create a channel, and then you start to create the insulation for that lava. And once the event is over, the lava will completely drain, but you're left with that hollow cavity. So we're seeing one that is starting to form in this area. And that makes sense, right? So you can see the darker pieces of lava solidifying on top of the flow, and it begins to insulate the internal magma. So allowing it to keep heat and to be able to keep moving. If you haven't been to an active volcano, you need to plan to do so because it's absolutely spectacular. In Iceland, this was moving into August, so temperatures are getting quite cold and breezes would come through the valley. And as the breeze comes through the valley, you get these waves of warmth. And when you have precipitation falling onto this lava, it begins to sizzle. And so you have this like really weird sizzling, cracking noise. You get this wave of warmth that overcomes you, and it kind of smells like charcoal. So it's a beautiful, beautiful experience that not even a drone video can help to capture. You notice my husband's getting a little bit more confident with his drone as we're approaching that. I think he backed off after that. Too close, too close. But where we're at today is there had been activity at the end of 2023 and up to today in the Sarvasingeti fissure swarm. So from 2021 to 2023, we're focused on Fagradalsfjall, but now the activity has shifted to the west. So the activity is in a different fissure swarm. The activity initially started on December 18th of 2023 and lasted for about a month. And this is just this particular initial cycle. What's important to recognize is that this fissure swarm is different. And the reason why it's different is because the area where it's happening on the Rainey's Peninsula is a low-lying topography. So the good thing about Fagradalsfjall was that it was confined within a valley. So there was some predictability of where you expected the lava to go. And also it was uninhabited. The challenge here is that there's this beautiful city called Grindavik in the path of this fissure swarm. Grindavik has about 3,700 people, and it's a coastal city, and they're mostly really a fishing village. So on December 18th, the fissure that initially opened was about 2 miles north of Grindavik, so you can see it off into the distance. The fissure was about 2.5 miles in length, and then during this episode, 2 smaller fissures began to open. So once there was activity, and again, the Met Office can not so much predict, but have an understanding of when a fissure eruption is going to happen because they're monitoring inflation and earthquakes. So they were able to evacuate the city of Grindavik, so nobody got in harm's way. But eventually, the lava overtook 4 different houses. This was a lot had to happen right within this month when this fissure opened. And one of the first things that the government did was help to build a barricade to protect a hydrothermal plant. And they did that because the hydrothermal plant produces water that goes to Reykjavik. And remember, there's 200,000 people that live in the city of Reykjavik that are dependent upon that, and it's wintertime. So they built a barricade, it worked. And later, moving forward, what has happened is they've continued to build some barricades. And the reason why they have done that is because there's still activity that's happening in and around Grindavik. So this is data starting in February of 2024 and going all the way up to present. This is again representing inflation and deflation models. So you have the last event that concluded, you have an increase in ground surface elevation, you have a fissure eruption that happens in March, and then you're starting to slowly ramp up again elevation, and there's expectation that there's going to be another fissure eruption. The Met Office calls it imminent. This map shows some of the ways that they're protecting the city of Grindavik. I put these red arrows on here to show you the position of these different barricades. And these are earthen barricades mostly. So they're using tuffra and sand deposits from parts of the island to prevent the lava from flowing and trying to redirect it into different situations. And so far, as you can see from this diagram, that has worked. So what's been really interesting about looking at these fissure eruptions on the Rainey's Peninsula is that this is the very first time that spreading ridge volcanism has been instrumentally monitored. So what we mentioned before is that there was Krafla, but Krafla, remember, was scenario 1 situation where you have a central cone volcano and a subsurface dike that's close to the surface. That was instrumentally monitored. We learned a lot about inflation, deflation, and earthquake swarms from that. But here we're looking at scenario 2. And so, because you can get so close to these, geologists have gone right up to the molten magma and been able to sample. So they're looking at true magma before it has even solidified on the Earth's surface. And they're coming up with a lot of really great data from being able to do that. So the first thing is that what we said was, prior to this, really this idea of scenario 2, magma coming from the deep mantle to supply these subsurface deep dike reservoirs was really a hypothesis. But what Bingman et al. 2022 was able to do is confirm that. So you might remember the terms lithosphere. So lithosphere represents the crust in the upper mantle. And then there's something that's called the asthenosphere, and that's the lower mantle. And the line that separates that two is called the Moho discontinuity line. It's a line really that separates the molten magma from those that's more plastic. And so what Bingman was able to confirm through really isotopic analysis is that this magma is in fact coming from more than 15 miles below the surface. And it is very similar to the basalts that we see on other parts of the Rainey's Peninsula. So it has acted as really confirmation. And it's an interesting discussion about the magma on the island of Iceland because it is very heterogeneous. So you have these things that are called ocean island basalts or hotspot basalts that are generated from a hotspot, and they have a different chemical composition than those that are being generated from a mid-ocean ridge basalt. And so you kind of see the interplay between these two around the island. And this helps to confirm that this is in fact deep-seated magma that's being brought to the surface from more than 15 miles in depth. And in working with Bingman, Call et al. 2022 was also sampling the magma as it's coming to the surface. They're looking at the solidified basalts, however, instead of the molten properties. And what Call et al. is looking at and focusing on are these, we call these phenocrysts. So basalt sometimes can be called vesicular basalt. It can have holes in it, so you can kind of see these holes in this picture, and that's a remnant of gases being emitted over time. And in some of these holes, they're being infilled with these phenocrysts that are called olivine, and those are the green ones, and the white ones are called plagioclase feldspar. And there's this concept in geology that's referred to as Bowen's reaction series. And Bowen's reaction series describes how magmas crystallize out of a body of magma. So when you find olivine, it's crystallizing at a temperature of 1400 degrees C. When you find plagioclase feldspar, it's calcium rich, it's solidifying at 1400 degrees C. So just the presence of these crystals tell us that the magma had to come from a deep depth. So it's confirming what Bingman had also suggested. The other thing that Call did is they age dated these crystals. So they isotopically age dated the olivine and plagioclase feldspar, and they come up with a date of 2 years. So what this tells us is that the reservoir was at least beginning to infill about 2 years ago. And so they're trying to use this as a predictive model of how long it might take for the magma to come up to the Earth's surface, based on the idea that you have crystals in the basalts that are forming that age date to about 2 years old. So this is just the findings that we're finding from Farga del Spajal. It's really too early to have publications from the Sarbanzageti fissure eruption, but it's going to be exciting to see what other new knowledge comes out of the research that's being done by Icelandic and other geologists. And so really, what does this mean for the island, and really what does this mean for Grindavik? If you've been on my tours, we have a good friend, and her name is Groa. Groa is Icelandic. She's from Keflavik. So I talked to her recently about the status of Grindavik. And what's happening is really the government really wants everybody to eventually evacuate. And so the government is offering money to purchase houses so that people can relocate. But they're talking about relocating the entire city. When I showed you the picture of the Rainey's Peninsula, I showed you that there are 6 different fissure swarms. So whether they're going to relocate on the Rainey's Peninsula or maybe somewhere further to the east in the eastern volcanic zone, I think that's yet to be determined. But the people that are staying in Grindavik have some confidence and some hope that those barriers that the government had built are going to protect their city. But there's continually magma that's coming up to the surface. There's continual ground inflation. And again, the Iceland Met Office really is predicting another fissure eruption probably within the next week or so. So I've had a lot of fun putting this presentation together. It gives you a real glimpse of what it means to live in the land, I think, of fire and ice, where there's 33 active volcanoes. There are these interesting and unique fissure eruptions in these two different scenarios, and the interplay between living in a place where the recurrence interval of volcanic activity is 1 every 5 years.
I'm gonna find something unusual in the bedroom.
So I'm happy to answer your questions, take your comments or your short stories. I think if you go ahead and put those, since we're a big group, go ahead and put those into the chat. I'll look at those. If you haven't had enough of me, you can find me as a featured host on the Weather Channel. There's a show that's called The Earth Unlocked that focuses on just this Earth processes. And season 2 is already aired. Season 3 launches in July. If you would love to go to Iceland with me or another tour, you can find us at Adventure Geology Tours. And I think I will go ahead now and take some questions from the chat. Or maybe there isn't so many questions yet in the chat.
I've got one, Tammy, but you want me to just, instead of typing it, you want me to just ask it?
Go ahead and ask.
So while you were talking, I was reminded of a volcano just north of Tonga in the Pacific Ocean that erupted in 2023 and 2024. And it was maybe an unusual eruption in that the seamount that caused it was below sea level.
Right.
And so it was a phreatic eruption to end all phreatic eruptions.
Correct.
It was the loudest recorded sound ever in the history of recording. Now that's what, 100 years out of 4.5 billion. So it's probably not the biggest explosion ever, but man, it in our lifetimes, it was a big one. Interestingly, while it did put some sulfur into the atmosphere, the more important effect it had, because the explosion was so huge, it put megatons of water vapor into the stratosphere way high up. And it had the opposite effect that sulfur dioxide and sulfur compounds, let's say, sulfuric acid, all the sulfur species in the atmosphere tend to cool the planet. And we frequently, you hear about those being compared to nuclear winter all the time. This one, though, actually warmed the planet a degree, somewhere between a half a degree and a degree and a half. So it exacerbated the problems with global warming. So it's interesting. We can't just paint all eruptions the same and say that they all cool the planet, because they don't. And there is an anomaly. If you look at global temperature records, people got really scared in 23 and 24. So the eruption was December 22 or 21. Was December 21, anyway, a couple of years ago. People got really scared because it looked like global warming itself was accelerating. I mean, I took notice, and that's why I kind of looked into this. But hopefully, fingers crossed, it's a bit of a temporary effect, and this year and the next years won't be quite as hot. We'll get back on the sort of normal upward rise of I just realized I had my video turned off. Sorry. We'll get back on the sort of, I'm using air quotes a lot. We'll get back on the sort of normal upward increase of temperature due to global warming. And maybe we'll look back on the last 2 years as being a non-human caused anomaly. But that's a fascinating eruption. It's Hunga Tonga, and you didn't hear about it much because it didn't kill a lot of people.
Yeah.
The island of Tonga had lots of warning. There was a tsunami. It wasn't real big. But different volcanoes do different things, and that's something we always have to keep in mind as scientists. We can't just say, well, volcanic eruptions cool the planet. No, they don't. They might, but they don't have to. Anyway, that's all I had.
And the sonic boom traveled like around the world twice, as I remember.
Oh my God. It was heard by people, not by instruments, by people 6,000 miles away.
That's right, like in Alaska. I do
boom.
remember. I do remember.
Yeah.
And then it changed atmospheric pressure. I think
Oh
they
yeah, absolutely.
had a huge reporting of that too.
Absolutely. I mean, it was worse than Wednesday morning after Taco Tuesday at my house. Anyway, thank you. That was a great summation of what's going on. It answered a lot of questions I had, and it made me curse the gods for not allowing me to see this thing. So thank you.
You're welcome. Any other questions? You can just go ahead and unmute yourself, I suppose.
There's a question in the comments.
Oh, do you want to read it, Joey? How do they collect and analyze the magma sample? Is that from Emily Grace?
Yeah. Hi.
Yeah. Hi, how are you? Emily Grace is one of my former students, and she also went to Iceland with me.
Yep.
So Bingman et al., very similar to Joey's apparatus with his hot dog stick. They're really just getting as close as possible and scooping it when it was molten. So just kind of looking for one of those Bohoihoi toes that still had some molten properties and sampling it directly. And then they analyzed it looking for oxygen 18 isotopes.
Oh, cool. Where are they relocating all those people to? They want them to move. Where are they going?
Well, I think right now they're giving them a fair market value for their house, and then the people have a choice. As you remember from being in Iceland, there's housing crunches. So I think that's one of the things that they're most concerned of. So exactly that, where are they going to go from where they're living at?
Yeah. Okay.
That's a big challenge. All right.
I've got one quick question, maybe. The flow out of these recent fissures that are threatening the Grindavik, are the flows pretty consistent, or are there forces that could make them change radically at different times? Because I know in Hawaii, when Mauna Loa was erupting, it was going to jeopardize the main highway that goes across the island, and everyone was saying, well, we need to build a barrier, and all the geoscientists were like going, yeah, that's just, there's no way a barrier is going to stop this flow. It's just, they were giving examples of how much the volume was, and they just said, per second volume was so huge, there was no way a barrier could stop it. But these ones, you said the barrier has worked, so is it unpredictable?
I think that is, I think they're doing it in good faith effort, if nothing else. And I think that for that initial flow, the city of Grindavik was about 2 miles away from the initial fissure. So I think at the end of that, at the end of the eruption, the flow had dissipated just enough. But you're right. I think there's a lot of unpredictability of how much magma is going to be brought to the surface and the location, because there's nothing to say that a fissure can't open underneath the city of Grindavik.
Oh, okay.
But yeah, I think if nothing else, I think it's a good faith effort to make the people who are remaining feel a little bit better about saving their houses.
Okay. Thank you.
You're welcome. All right, everybody. Well, thank you. I've had a great time. Keep in touch, and we should do this again.
Well,
Yes. Thank you.
Good night.
thank you, Tamie.
You're
Appreciate
welcome.
it.
Thank you.